Welcome to this explainer. Today, we're diving into a massive, completely invisible machine that literally drives our entire planet. We're talking about a system so vast and so powerful that it dictates our climate, controls exactly where life thrives, and basically sustains all of our global ecosystems. We are talking about the hidden heartbeat of the ocean. Now, when we look out at the ocean, right, we usually just see the surface, maybe some waves crashing on the beach. But underneath all of that, there are these massive, invisible rivers constantly flowing all across the globe. And they aren't just random, chaotic movements of water either. They are part of a highly organized, relentless mechanical engine. So, what actually creates and powers these global currents?
Okay, section 1, the forces of motion. Let's just jump right in and look at the primary forces that act like the ignition keys to start this massive ocean engine. Believe it or not, it all starts with the sun. Solar radiation heats up the water, causing thermal expansion, especially right at the equator where that heat is super direct. And get this, it creates a literal physical slope in the water. Because of that heat, the surface of the ocean at the equator actually sits about 8 centimeters higher than it does out in the middle latitudes. Wild, right?
But that solar energy is really just the first piece of the puzzle. The ocean's engine is actually driven by 4 primary forces that get all this water moving. We've got the heating from solar energy, the push of the wind, the steady pull of gravity, and finally, the rotation of the Earth, which is known as the Coriolis force.
Let's see how these 4 forces actually interact, because it's pretty brilliant. So the solar heat builds that 8-centimeter slope we just talked about. Once you have a slope, well, gravity kicks in, naturally pulling the water down that hill, so to speak, and creating a flow. At the exact same time, wind is blowing across the ocean, and the friction there pushes the surface water right along with it. And then the Coriolis force steps in. Because the Earth is constantly spinning, this force makes that moving water veer off course, pushing it to the right in the northern hemisphere and to the left in the southern hemisphere.
And when you combine the whole shebang, that thermal slope, the wind's push, gravity's pull, and the Coriolis steering wheel, you get something absolutely incredible: gyres. These are massive, closed-loop accumulations of water that completely dominate all of our ocean basins. It's basically a giant, natural, circular current. Moving on to section 2, surface versus deep water. So now that we know what creates these huge gyres, let's see how depth completely changes the game. Now, you might picture these massive global currents roaring past like water out of a fire hose, but that's not quite how it works. A current is usually strongest right up at the surface, where the wind catches it, but it actually loses strength and speed the deeper down you go. In fact, despite their immense power, most of these currents are just cruising along at speeds of 5 knots or less. It's a very slow, steady, and relentless march.
And to really put the sheer scale of the ocean's engine into perspective, check this out. We spend almost all our time thinking about the surface of the ocean. But surface currents, which happen in the upper 400 meters or so, make up only 10% of the moving water. The other massive 90%, that's moving as deep water currents, entirely hidden away in the dark, miles below us.
Which naturally leads us to section 3, the density driver. How does that deep 90% move at all if the wind can't even reach it? Let's take a look at the vertical mobility of this engine. Down in the deep ocean, density dictates absolutely everything. And density is driven by 2 main things: salt and temperature. High salinity, freezing cold water is incredibly dense, so it literally plunges straight down. On the other hand, water that's fresher and warmer is much lighter, so it stays perfectly buoyant up at the top. This simple density dynamic sets off a continuous global loop of vertical movement. It's literally like a giant underwater conveyor belt. Up at the freezing poles, the cold water gets super dense, sinks all the way down to the deep ocean floor, and slowly creeps along the bottom heading toward the equator. And to fill the massive void left by all that sinking water, warm surface water from the equator travels outward, flowing along the surface toward the poles to replace it. Down at the poles, up at the equator, just over and over again.
All right, section 4, warm and cold currents. It is super fascinating to classify these surface currents by their temperature, and especially to look at where they actually crash into the continents.
Let's zoom in on the low and middle latitudes, so basically the tropical and temperate zones of the Earth. Notice the really distinct pattern we have here. Cold currents, which pull freezing water into warm areas, are typically found hugging the west coasts of our continents, and that's true in both hemispheres. On the flip side, Warm currents, which push warmer tropical water into cooler areas, are usually observed washing right up against the east coasts.
But watch what happens when you move further up the globe into the higher latitudes of the northern hemisphere. The whole pattern completely flips. Suddenly, you have cold currents running down the east coasts and warm currents traveling up the west coasts of the continents. It is an incredibly precise planetary system, and it literally dictates the coastal climates for everyone living there. Finally, let's head into Section 5, where the waters mix. This is where we see the ultimate biological payoff when these carefully orchestrated systems finally meet.
So, what actually happens when warm and cold currents collide? Just think about it for a second. You have this massive, dense, freezing, nutrient-rich water slamming into lighter, warmer surface water. It's not just some cool physics phenomenon. It creates a literal biological explosion. Here's how it plays out. When these warm and cold currents mix together, the violent churning action replenishes the oxygen levels in the water. That fresh oxygen, combined with the sudden temperature shift, creates this totally hyperproductive environment for plankton blooms. And those massive amounts of plankton, they are exactly what sustains huge, thriving fish populations. Which brings us right to the core takeaway of this entire explainer. These invisible physical forces, the 8-centimeter equatorial slope, the sinking salty water at the poles, the spinning gyres, they directly dictate human survival. Because of those massive plankton blooms, the absolute best fishing grounds in the entire world exist almost entirely in these specific zones where warm and cold currents mix.
I want to really emphasize this by sharing an exact quote drawn directly from our source material. It says, "The mixing of warm and cold currents help to replenish the oxygen and favor the growth of planktons, the primary food for fish population." I absolutely love that because it perfectly illustrates how abstract ocean physics, like gravity and the Coriolis force, are deeply and directly tied to the biological foundation of the entire ocean. So as we wrap things up today, I want to leave you with one final, kind of provocative thought. We've seen how solar, heat, wind, and density differences power this continuous, life-giving conveyor belt that literally feeds the world. But if global temperatures shift, or if the salt balance gets thrown off, and this invisible circulating machine starts to slow down, what happens to all the life that depends on it? It is an incredibly vital but fragile engine, and understanding how it works is absolutely the first step in protecting it. Thank you so much for joining me for this explainer, and keep questioning the world around you.